during or at home. Okay. So then I'm going to switch again to the presentation. Let's see if it works. Thank you very much. Playing with two screens is never. Okay, so this is going to be the outline of this part of the talk. I'm going to, as I said before, I'm going to talk about the bad guy in this game, which is the speckled noise, and the guy that makes our life a bit difficult. Okay, so as I presented before, here we have as our image, okay, with the polarimetric information color code. Here we have an orthophoto of the same area. So basically here you can see that this SAR image completely reflects what is in reality. But what is a speckle? Okay. If now I take a closer look to the image, and in here I take the intensity of the BB channel, if I zoom to any area of the SAR image, what you can see in the image is that it has this salt and pepper aspect. Okay, this is what we call a speckle noise. It's a kind of noise, but in reality, as you will see, it is not a noise. It is a proper electromagnetic measurement. Okay, the problem is that it's so random that the only way to tackle this problem is to assume that it is a noise, and therefore to consider the idea that we have to remove it. And as you will see, we will establish a connection, or the idea presented at the end of the last presentation, where we lost the connection between the one part of the descriptors and the other part of the descriptors. As you will see, the process producing this disconnection and the need to average the data is this speckle noise. Okay, so just to clarify, speckle noise is this salt and pepper aspect of the SAR images. So how do we create the art of the speckle noise? Remember that before I described the SAR image as a filter. It has an impulse response. So therefore, the SAR image is nothing more than the convolution of the real reflectivity, the 2D convolution of the real reflectivity with the impulse response of that system. Okay, this is how we create SAR images. Okay, in X and R, azimuth and range. Okay, if we go to the digital world to make it more simple, basically we can transform it into this way. So basically this addition, what it makes in here is that the SAR image is nothing more than a weighted sum, okay, of all the individual scatters covered by this impulse response and weighted by the weight of this function. Okay, so everything depends on the number of targets we have. What happens? L, the number of targets, can be a deterministic quantity. What happens if L is equal to 1? We have one target. Okay, so therefore we have a deterministic target, and then we go into the idea of totally polarized wave. But L can be larger than 1. Okay, if L is infinite, assume infinite, we have plenty of targets, we have what we call fully developed speckle. Okay, so therefore, you will see later on, we characterize the SAR image by a Gaussian distribution, but bear that in mind. So we can go between these two models: no speckle, L equal to 1, L infinite, fully developed speckle. We can have something in the middle. That's the most difficult problem. Okay, When you have 2, 3, 4, 5, 6, there is no even an analytic solution of this problem. So for instance, yesterday in the chapter talk, we were discussing about that. We had some discussion about urban scenarios fall into this case. That's why it's so difficult to analyze urban scenario. So the solution to analyze urban scenario is to increase spatial resolution. Why? Because increasing resolution, I can go to this situation in here. Okay? But for natural targets, okay, we have this. Forest, crops, deserts, whatever, they fall in here. L can be also stochastic, can have a distribution. Won't enter into this case, into this presentation, but therefore is when we have texture, data texture. Okay? So this is the way to analyze speckle noise. So let's go into analyze this guy here. Remember, we are complex.
Partially developed speckle, you have said that it's not solved.
It's not solved analytically.
But fully developed speckle is a Gaussian model.
It's a Gaussian model, yeah. I will come to that later. You will see, okay? It's a constructive process, okay? Okay. So our image is this. So the value of each pixel is created in this way. So if L is equal to 1, we have one vector, which is the response of the target. And we can get some physical information. What happens when L is infinite? What do we have? We have the addition of complex vectors. We have a random walk. Okay, here it's cut, but it doesn't matter. Okay, the idea is that some images have an amplitude and a phase, real and imaginary part. How this complex addition can be? Which are the two extremes? One extreme is that all the vectors sum coherently, all have the same phase. So therefore, we have a constructive process. It's a constructive interference. The opposite is to have a destructive interference. Okay? I can have many of them, but the total sum can be 0. So, what is a speckle? The bright points are those points in which this sum is constructive, and the dark points are where this sum is destructive. Okay, but it's not a noise, it's a proper electromagnetic measure. If my target doesn't move, and I repeat again and again and again the same measure, I obtain the same result. So the question is why we call it noise. Let's go in this case. So what happens if L tends to infinite? For the real part, we take this, and for the imaginary part, we have this, okay? So the idea is the following. We have fully developed speckle, okay? So the bright points are where we are constructive, the dark points is destructive. So okay, we have here, we have a speckle, okay? If we have bright points, here we have a corner reflectors. So what do you see here? You see a cross. The cross is nothing more than the double sync we saw before. Okay, so for in this particular case, we don't have a speckle. So in some situations where we have a speckle, and in some situations we don't have a speckle. So the speckle is the interference pattern in the image, because we are using a coherent systems. With lasers, you have exactly the same, because the light is coherent, so you see a speckle with laser. Okay, so we can talk about hours if you want, of a speckle in lasers. Okay, so what happens? We have discussed that we form the image in this way. Okay, complex addition. So what happens? The real and the imaginary part. What happens is L is infinite. If L is infinite and we take this hypothesis that the amplitude and the phase of each individual target is independent, and the targets are independent between them, we can call the central limit theorem. And therefore, we can model the SAR image as a complex normal distribution for the real and the imaginary parts. Therefore, the real part will follow a Gaussian PDF, the imaginary part will follow also a Gaussian PDF, and the correlation between the two is equal to 0. So remember, a speckle, I mean, this is just to know it. A speckle is not noise, it's a proper electromagnetic measurement. The problem is that speckle depends on the microscopic structure of the target. And this can be so complex that the only way to handle this complexity is by considering the distribution of the data. But remember, a speckle is not a noise, it's a proper electromagnetic measurement. I mean, if you measure in a communication system additive Gaussian noise, each time you measure the system, the noise is different. Okay? In this case, if everything stays the same, the measure is the same. The fading pattern is the same, so therefore it's not a noise. The problem is that it's so complex, okay? It's so complex, this complex addition, that the only way we can tackle, the only way we can understand this complex addition is through considering as a noise. So therefore, the information is no longer in the individual value of a pixel, but on the distribution, therefore on the moments, on the mean and the standard deviation. Okay? Every time we work with a distribution, we are interested into the PDF, and if we don't have access to the PDF, we have access to the moments. So therefore, the real imaginary part follows a Gaussian, a zero mean Gaussian, by the way, okay? And both are uncorrelated. Making the... When? Basically, you assume it everywhere except on bright points. You assume everywhere. You can assume it everywhere. Everywhere where you have a speckle as a first order approximation. We could talk about other more complex distributions, but in general, you can assume it everywhere. In homogeneous areas. Sir?
Here IIT, independent or identical distributed, all pattern, all noise pixels. They are IIT. Can we assume that to be IIT?
IIT, what is?
Dependent and identical distributed.
Let me continue because I will tackle this issue later on. Okay, I was here. So I can make the transformation of variables, so therefore I can find the distribution of the amplitude. I mean, and the amplitude of the SAR image is essentially a Rayleigh distribution. The intensity is an exponential, and the phase is uniform. What does it mean that the phase is uniform? That the phase, in the case of distributed target, has no information because it's uniform. All the values have the same probability. So a single value has no information. How they look like? So this is how the distribution of the amplitude looks like. So if you take a SAR image and plot the distribution on a homogeneous area of the intensity, you will end up with a distribution like this. If you go to the exponential, you will go to the intensity, you will go here, and if you go to the phase, you will end up with a distribution like this. Okay, therefore, if we recall what I explained before, my polarization is not fully polarized, it's partially polarized, it's random. And the randomness comes to this speckle noise. Okay? Okay, so therefore, important considerations. A speckle is a deterministic electromagnetic effect. But due to the complexity, the only way I have to deal with that complexity would be to analyze statistically. I always quote this example. Imagine that you are measuring a tree. If you are able to know the trunk, the branches, and each of the individual leaves, you could interpret deterministically because you know all the position of the targets. But I don't, in a forest, I don't have one tree, I have 1 million of trees. So it's impossible to know the position of all the leaves of 1 million trees. So the way to deal with that complexity is to go a step back and to assume that these
They are uncorrelated.
yes, they are correlated. If they
Correlated. Using that assumption,
no, because you would need to know the position of each individual leaf in each individual tree, and this is impossible to know.
yes, yes. So that is why you can assume it to be uncorrelated, huh? Because you don't have that information. That is why you
Incorrelated, what do you mean with incorrelated?
scattered components from different targets.
No, within correlation between targets, you assume that all of them do not behave in the same way. That's the need of uncorrelated. Imagine that all the pixels, sorry, all the targets will move into the same way. That we were talking about a different thing, because it's something deterministic. All of them move in the same way.
Go back to the previous slide. Previous slide. Again, go back. Yeah, here. Here you get an uncorrelated point vector. What is then?
That they behave independently. That this leaf does not behave as the other leaf. They are completely uncorrelated. They have no relation between them. I mean, this is not totally true, of course, because if there is wind, all the leaves move in the same way. But for the sake of simplicity, I have to do this, okay?
Basically to model it.
Yeah, to model it. Yeah, let's assume it. I like it.
Simplify it in a form of a model.
Yeah, a simple model. Okay, I mean, we could discuss, okay, I don't like this model. I would like to go to the deterministic problem. Okay, go ahead, analyze yourself. You will need 3 lives to analyze all the problem, you know? So we need to simplify, otherwise the problem becomes impossible. The idea is okay. The idea is how simple or how complex is your model. Okay. The idea is that the complexity, my model has to be sufficiently complex to model my physics, but also not too complex to allow the inversion of the model with the measures I have. I mean, I cannot suppose a model of 10 parameters when I have only 2 observables. So it's a compromise. Everything in this life is a compromise. So this is true.
When you say phase as unit,
Yeah.
In a given scatter cell, then you have L much greater than 1. And all the scatter elements, whatever is coming, the waves which are coming from each of the scatter, do you mean to say that all the phase will be same, or what is that? How do I interpret that phase as unit?
This is, sorry. Okay. Sorry. Here, I interpret that any phase value has the same probability. So it means that there is not a privileged phase somehow. So therefore, it means that as all the values have the same probability, the only thing I have is noise. Okay? The only thing I have is noise because everything has the same probability. Okay? So, speckle is a deterministic electromagnetic measurement. It's a deterministic, it's not a noise, but the only way to tackle it is to consider it as a noise. Okay, so therefore, okay, if it is statistics for a distributed target, okay, the actual value of a given pixel has no information at all, because the information is on the statistical moments that define the distribution. That's why I need to filter. Filter is nothing more than estimation. Okay, so what is the information then? So let's go to intensity. Phase has no information, the intensity is exponentially distributed. So it's here. Okay, so therefore, if I take the different moments, if I take the the expectation has this value, which is 2 sigma square, and the standard deviation is also 2 sigma square. Okay, so therefore, okay, the information is not on the value of a given pixel, but into this distribution, into these moments. Okay, so therefore, what we need to find out is this parameter sigma, which at the end defines completely the distribution. And this sigma is nothing more than the radar cross-section. So therefore, if we have the intensity, we have a parameter that is the useful information, and the other thing is the noise. The noise is the variability across this mean value. So how do I represent that? Okay, with a noise model. Okay, so let's go to this. Okay, I have this intensity. Okay, where the expectation is like this and the standard deviation is like this. I mean, what happens if I normalize the intensity? I mean, I assume that this value is equal to 1 and this value is equal to 1. Therefore, I end up with this normalized exponential distribution. So if I combine both the noise and the distribution, I end up with this model for the spectral noise. So I can represent the intensity of a SAR image as the product of my radar cross-section, okay, multiplied by the noise. This is where the information is. This is what I want to eliminate. This is a speckle. This is the useful information. Okay? It's clear? So I want to identify that. So this model is particular. It's not the classical additive noise model. If you are engineer, you are super used to Gaussian, white noise, additive, blah, 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 okay? And the way to correct that noise, I simply increase my power because I increase the signal to noise ratio, right? This thing cannot be done in radar because if I increase the power, I increase the variance. So I cannot fight speckle noise through increasing power because the signal to noise ratio is constant. So therefore, I need a second way to remove that noise, and this is the filter. This is what we call the multiplicative speckle noise model. This is why we say that the speckle is multiplicative. This is how a speckle affects the information I'm interested into. If I put here, this is a real case. I take this homogeneous area, I plot for the two channels, HHPV, the standard deviation against the mean, all the points fall into this line, which is the one-to-one line. So what does it mean? It means that the standard deviation to the mean value. So therefore, noise is multiplicative. So in this particular case, okay, the model is almost Gaussian because all the values follow this trend. Okay? Okay. How do we calculate that? Or how do I measure the speckle noise? Okay? What I can make is to calculate the coefficient of variation, which is the standard deviation against the mean value. Okay, so the standard deviation against the mean value, okay, if I plot it, this has a value equal to 1. And I cannot change this value by increasing the power, because if I increase the power, I increase the standard deviation, and it's always 1. If I make the inverse, the mean to the standard deviation, I obtain what is called the equivalent number of looks. Is the quality of the image. Okay? The worst case is ENL equal to 1. So given this equation, how I increase the equivalent number of looks? The only way is by keeping the mean value and reducing the standard deviation. So the only way I have to reduce the standard deviation is to limit the standard deviation. I can limit it with a filter. Okay, so one of the things that is interesting to see is this is one simulation I did in the past. Okay. Sorry, I'm going to close this. Okay. Simulation I did in the past. Okay. Oh, sorry. I wanted to. Good. That's okay. So let's look into the detail of the number of targets. Okay. So if I calculate the intensity by assuming in each pixel I have only one target, I obtain this. Okay, I obtain the real part and the imaginary. Here my target was at only real part, so it's a delta. Okay, it's not stochastic, it's totally deterministic. This is a point target. This is totally polarized web. What happens if I increase the number of targets? If I increase just only 5 targets per resolution cell, per pixel, what do you see? You see this fading pattern. Okay, already 5 targets induce a fading pattern. The problem is that this is the plot, the intensity, the histogram of the intensity, and this is the histogram of the real and the imaginary part. And if you see, both are not equal. Okay, which violates what I imposed before, because the Gaussian model is only true when I assume a large number of targets. So let's do the same. Let's go to 10, to 100, and 1000. Okay, so for 10 is still difference between real and the imaginary part. This is partial developed speckle. This is partial developed speckle. This is partial developed speckle. This is fully developed speckle. You see that the distribution of the real and the imaginary part are the same. So only in this case, I could assume, okay, that I'm in front of a situation of fully developed speckle. All this is partial developed speckle. This is no speckle. And this is the result on the intensity, the histogram of the intensity, the histograms of the real and the imaginary bars. So where I put the limit? Around 1000. Maybe it could be also true, but to see which is the effect. What happens if I go to a stochastic? Then it appears texture. So therefore, my model is still multiplicative. I have the radar cross section, I have the noise, but I have a third signal, and this signal is texture. It's I analyze a mid-level of randomness, which is low frequency, is the texture. Okay, so we have The coarsest scale, which is the main reflectivity, is the constant value. The finest scale, which is the speckle, and one intermediate scale, which is the text. Okay? Yeah, I assume the same type. Yeah, for my simulation, I assume the same type of target. But I think it wouldn't change much if you change the type of target. Except if you assume one of them dominant. If there is one dominant, then the model is a Bayesian model, which is a bit different, okay? I mean, you can make it this very complex, huh? So, a speckle. We have analyzed a speckle. One image, one single image. But remember, polarimetry is a collection of images, is a vector. What happens in that case? Okay, so when we are in a multidimensional signal, a speckle, we have a vector HH, BB, HB. Okay, so therefore, if the target is a point target, therefore the vector K is deterministic because we are under a target. So therefore, this K vector, okay, contains all the information to characterize the target. If we have a distributed target, if we have a partially developed, totally developed speckle, and if we have a partially polarized wave, then K is a random vector because each of the components is random. The question here is where is the information in a vector? Okay? Which are the first and the second order moments of a vector? That's the question. Remember, for a scalar, the first order moment is the mean value, the second order moment is the standard deviation. So how these concepts generalize for a vector? Okay, so we start with the same, okay? Let's make this hypothesis. Let's assume that each SAR image follows complex Gaussian distribution as we did before. Okay? I mean, this is one hypothesis I can play with. The images are these each images and each image distributed as we said before. Okay? Real part Gaussian, imaginary part Gaussian, uncorrelated. I have no longer one image, I have three images. So which is the distribution of the vector? Well, let's play with this hypothesis. Let's assume, okay, that these images are independent. So the total PDF is the product of all the PDFs. Okay, because they are independent. So the PDF of the vector is the product of the independent distribution of each component. So therefore, I end up with this distribution. Okay? Okay, I calculate the first order moment. 0, because the components are 0. The SAR images are 0. What happens to the second order moment? The second order moment of a vector is a covariance matrix. What happens? If I assume this hypothesis, the only possible covariance matrix that can model this situation is a covariance matrix proportional to the identity matrix, which indeed is a very poor matrix. It contains no information at all, okay? So we need to generalize, because if you remember what I explained in the first part of this tutorial, my information is not only contained into the intensities of the SAR images, but onto the correlations. So I need to allow general coherency matrices, not only diagonal coherency matrices. So this means that I need to allow these components of the vector, the SAR images, to be correlated. Okay, so therefore, I took this distribution, which is the general Gaussian distribution for a complex vector of m components in three components, sorry, in this particular case, which allows any covariance matrix. So what I have in this matrix, I have the diagonal terms, which basically represents the intensity, and I have the off-diagonal elements, which represent the correlation of the images. So as you see, this model is totally different from here. In here, I'm assuming that the SAR images have the same power. I could assume different powers, but it's still proportional to the diagonal. In the general case, my matrix is like this. It's a full matrix. Okay? What I need to do to the Gaussian model, I mean, the idea to use the Gaussian is its simplicity, and it's very elegant in the sense that what do I need to characterize a distribution? I need the distribution itself, or what they call it, all the moments of this distribution. The advantage of the Gaussian distribution is that I only need the first order moment and the second order moment to characterize the matrix. So if the first order moment is 0 and I have only the covariance matrix, finally only the covariance matrix characterize the distribution. And higher order moments are a function of this matrix. So this is the beauty of the Gaussian distribution. I only need to play with covariance matrices. Okay, so the covariance matrix has this shape in here. So the diagonal element contains the intensity, the off-diagonal elements contains the correlations. And why I need to make this expectation? Because of the fact that this data, okay, these guys in here have speckle noise. That's why I need the expectation. The covariance matrix on distributed scatters only takes sense when there is an expectation, because it's a moment that characterizes the distribution of the data. Okay? So what I have my distribution, okay, which is this, first order moment equal to 0, and this is the covariance matrix. Okay? So all the information characterizing the set of 3 images is contained in the covariance matrix for distributed targets. So if you remember, I end up the last presentation with that map of descriptors. And if you remember, I came also to the idea of covariance matrix from polarimetry. In here, I have come to the idea of covariance matrix through the statistics. So basically, the fact that this K vector is random, I need this expectation to remove the speckle noise. So what is implicit here is the fact that I'm breaking the relation between the second order moments, okay, the covariance matrix, and this polarimetric measurements, because the polarimetric measurements are done in here. So, first of all, the polarimetry gives me the physical interpretation of this matrix. The statistics helps me to interpret this matrix statistically. So I can combine both the statistical description through the Gaussian distribution and the physical information through the polarimetry. Okay? So I have come to the same point from 2 different things. I have come to polarimetry. Remember, I defined the covariance matrix to the vectorization of the scattering matrix, and also I came, or I needed to introduce this matrix to characterize the distribution of the data, and all of them is 2 interpretations of the same quantity: a statistical representation, a physical interpretation. Okay. So the off-diagonal elements contain the intensity, as we know. The off-diagonal elements are these guys in here, but the most important thing is that these guys can be also normalized. So we go to the normalized correlation. Remember, when I went back, polarimetry is not only contained into the intensity, but also into the correlation of the SAR images. And this is the information given here. When I plot these color images, which are very nice, I'm only representing this part of the information. But polarimetry is something more than just colors, nice colors. Polarimetry is this and these guys in here. Is intensity plus correlation. And by the way, these guys, the phase of these guys are the most important radar observables. Okay? So let's do maps. I like maps. So we have multidimensional SAR data. For our case, multidimensional means polarimetry. So what do we have? We have the scattering matrix. Okay, what the radar measures? I can arrange it into a vector. Okay, from here to here, I'm just generalizing, but it doesn't, is not a problem. Okay. Of course, I can make the outer product of this K vector to generate the covariance matrix for polarimetry or for a collection of MSAR images. Okay, so when I have a point target, when my wave is totally polarized, these descriptors are complete to describe the physics. I have no speckle in that case. They are not random. What happens when I have randomness? When I have randomness, the mean value is 0, so it gives no information, but the covariance matrix, which is in essence the second order moment of this K vector, is different from 0, and all the information is contained. So how do I characterize the statistics of the data through the covariance matrix? How do I interpret the physics? Through polarimetry. And everything is linked by the distribution of the data. So when I'm dealing with distributed targets, with forests, crops, ice, glaciers, whatever you want, something natural, I have to go into here. When I analyze point targets, I can stay here. And the interpretation is different. Here, data are deterministic, so the physical interpretation is total. When I am in a distributed target, the information takes sense from a statistical point of view. And as you've seen, I lose the connection of this matrix with the original measurements because of the expectation, because of the filtering. Okay, so how do I estimate that that information? As you see, the covariance matrix takes sense only through the expectation. So what does it mean, the expectation? Expectation is the estimation of a value. So the expectation is nothing more than a filtering process. That's why we talk about speckle filtering, speckle reduction, estimation. How do we do that? The problem doing that, as I presented before, is that I do not live in a world where all my things are point target or where all my world is distributed target. We have the mixture between the two. So I have to cope with that complexity. For instance, in this particular case, I have homogeneous areas, okay, where the information is contained on the statistics itself. I have point targets. The point targets do not need filtering, okay? So I have to keep that filtering. The reality is that I have a mixture of all these things. So how do I deal with that? And which are the effects of this heterogeneity, which is on the basis of the speckle filtering? Okay? How do we estimate? This is just a technical thing. I assume ergodicity, wide sense stationarity. The most important is this, homogeneity. I need that all the pixels belong to the same class, either to the same type of target, either to the same distribution. So if I assume all of them, okay, the most standard way of filtering is the multi-look, is a spatial filter. I take one set of spatial filters and I take the mean. And the most important thing is that for this to take sense, all the elements need to be processed in the same way, because otherwise I would change the statistics. Okay. Therefore, and this is where also starts to become difficult, the estimation of this covariance matrix is at the same time a random variable. Okay, it's a random matrix. So it is possible to see that this estimated covariance matrix is distributed according to the complex Wishart distribution, which is this expression in here, okay, and is only valid for n larger or equal to 3. So therefore, the statistic estimation in polarimetry only takes sense if I filter more than 3 pixels. If I filter 2 or none, it makes no sense. Indeed, this distribution is not defined. And okay, and also the most important characteristic is that this distribution, despite it is super complex, it depends only on the covariance matrix, on the true polarimetric. So we don't add new information. So therefore, filtering does not change the polarimetric information because it only depends on this covariance matrix. Okay? So this is the map we have again.
Complex Wishart distribution, the previous slide.
No, the complex Wishart distribution is that when I estimate a random variable through a limited process, itself, the variable I'm estimating from a random sample is at the same time a random variable. And the distribution of this estimated random variable is distributed according to this Wishart distribution. So the estimated covariance matrix follows itself a distribution. Let me go to the next slide. Okay, so I have a single SAR image distributed according a complex Gaussian distribution. I have my vector, so therefore this vector is characterized by this complex Gaussian distribution, which is characterized by the covariance matrix. Okay, until this point it's okay. The problem is that I need to estimate this matrix. I estimate this matrix through a limited filtering because it's limited by the number of samples. Okay, if I would have infinite number of samples, no problem. But I need to estimate with a limited sample number, a limited number of samples. Therefore, this matrix at the same time itself is a random variable because the estimation is not perfect because I do it with a limited number of samples. So therefore, the distribution of this estimated covariance matrix is given by the complex Wishart distribution. That's why I have these two, because I'm estimating a random variable. Okay? So, okay, let's do that. Assume that I have a boxcar. Okay, I have this original image, and in here I have estimated the matrix through a 7x7 filter. $1 million question. You will see now. Okay, this is another. We could talk 20 hours if you want about that, but you will see which is the effect. Okay, perfect. This image has lost the speckle. Something that may seem super stupid. The filter has not changed the colors of the image. So it means that it has not changed the polarimetry, because the RGB establishes the relation between the channels. If I would process the channels in a different way, I would change the relation between the variables. So therefore, if you read papers about polarimetric speckle noise, okay, the first question that I, as a reviewer, would ask is, do your filter change the polarimetric information? That's the first question you have to ask. Okay, that's why all the elements have to be processed in the same way. Okay, perfect. Life is easy. Okay, let's go to Zoom. Perfect. Okay, on the homogeneous areas. Okay, it's perfect. I remove noise. Life is easy. What happens on the point targets? These are corner reflectors. What happens into this? What happens in this case? You lose the spatial resolution. So I spend $1,000 million in one machine to obtain very high spatial resolution, and with a stupid filter, I lose the value of everything. So that's, I mean, and sometimes I like to joke because, but you see the extreme, you go to the extreme and, okay, I spend 1,000 million euros or dollars, whatever, I don't care. And you lose the spatial resolution, okay? I have 10,000 engineers working into that to arrive to this. So no, you will have to do it something a bit more complicated. And there is a solution. First of all, most important thing, you don't change, again, you don't change the colors. Okay, you don't change the color. This is very important because you don't change the polarimetric information. Here, you have a parking lot. You see that basically you see the differences between or the roads between the cars, which are parked, you lose that information. So, I mean, no, I mean, I want something with a spatial resolution. So what I have to do, I need to make intelligent filtering. I mean, whenever the filter detects an homogeneous areas, there the filter has to filter as much as possible, but whenever I have a point target, the filter has to do not filter, to keep the spatial resolution. So it's a compromise. Okay, and nowadays there are many ways to tackle with this compromise. Okay, the first thing is what is called.
The last one, this is moving average box.
Yeah, it's moving average box. It's moving average box. Yeah. So what you see here is the impulse response of the filter, which is a 7x7. What happens if I would put 20x20? I will say a square like this. So that's the impulse response of the filter. So therefore, a speckle has to be a nonlinear process. Okay, I need a filter which is not defined by an impulse response, something which is nonlinear. Because in this case, it's linear because I apply the convolution.
Same weights.
Sorry?
Applying same weights to everything.
Yeah. It cannot be done because a convolution means that the filter is always the same. Okay, so I need a filter which impulse response adapts to the pixel, therefore nonlinear. Okay. So, I mean, there are many different ways. If you want, you can go to the literature. Okay, so the best is just to go to some simple filters. Okay, the most simple filter is the Lie filter, which basically through all the equations, the filter is able to analyze if it is in a point target on a distributed target, and the effect is the following. The effect is the following. Okay, you have the point target, the original image. This is the result. Okay, of the convolution. Okay, and finally, this is the result. So as you see, on homogeneous areas, they are more or less the same. On point targets, you keep the spatial resolution. You keep the details. You can also extend that filter to the case of polarimetry. You no longer estimate one variable, you estimate a matrix. Okay, you can adapt. There are different policies to adapt. Okay, details are not interesting. The point is that the filter is able to adapt to the heterogeneity of the data. So let's go to the results. This is the original. This is the 7x7. This is the leaf filter. If we go to the detail, you see the results. Okay, this is the original. This is 7x7. How you use the details, especially in these point targets or in this urban area, and how using the leaf filter, okay, you keep the details of the point targets. And the most important thing, again, the filter, as you see, doesn't change the colors. So it means it doesn't change the polarimetric information. If you define a filter and the filter changes the colors, throw the filter to the trash because it's nonsense. Because you change the polarimetric information. Okay? Questions?
As resolution is increasing, the points are also tending to become more like continuous.
Yeah, that's a problem. If you increase the resolution, you will start or you abandon the idea of totally developed speckle, and you enter into a game of partially developed speckle, or where you almost all your target, all your pixels are have no speckle at the end.
But at higher resolution, don't the point what are the point targets, they tend to become more like homogeneous because just have more pixels?
No, in the ideal case that you have such a high resolution that you have only one target per pixel, you have no speckle. You don't have to filter. The problem is that you are in the middle. You cannot be that. As I said before, the worst case is that in the middle. Okay, because there is not a complete physical interpretation, but also there is not a complete statistical interpretation. So how to extract the information, this is very complex.
That is the more common situation for urban.
That's the most common situation for urban areas. So urban areas, sometimes you filter, but it's a super mild filter, super small filter. You lose the details of the urban area if you filter. Okay.
Speckle noise is basically used to minimize. Filter is used to minimize the speckle noise so that the target looks more prominent. Otherwise, from the original RGB to the refined deep filter, speckle noise is smoothened.
Yes.
But what is the use? The targets are.
What do you mean? These targets?
Yeah, targets remain the same.
Targets remain the same because they are not filtered.
So what is the advantage? It's the reduction of the speckle noise.
The reduction in the speckle noise?
The target looks more prominent.
No.
Keeping the target intact. Yeah, reduction of the speckle noise, keeping the target intact.
Exact.
It's like,
Keeping the targets. No, I mean, using your word, prominence. The point target. Sorry. The target has the same predominance here and here. So the effect of the filter is only to reduce the variance, but I cannot change the predominance of the point target because it would mean that I change the target itself.
what I meant is signal to interference level, interference noise ratio is increased. From signal processing point of view, interference.
Because in this point I don't filter. Here in the extreme I don't filter. So I keep the point as it is. I mean, life is a bit more complex, but in the extreme case, I don't filter this. I keep this because this has no speckle. This has a speculum.
If I try to explain what
Yeah.
he's trying to say from the perspective of signal to interference ratio, in the sense that signal is that point target and interference is the.
Okay, in that case, yes. If I compare this with this, yes. Okay, I agree. Yeah, in that I agree with you.
That is the.
Yes,
Yeah, yeah. But from my point, this is personal. This is one target. This is another. This is glass, and this is a. I mean, this is glass, and this is a corner reflector. Two different things.
Talked about fading random variable.
Sorry,
You talked about fading random variable.
varying the number n.
No. Fading signal, fading the spectrum.
Yeah.
So is it somewhat related to this filtering operation? Like if you use a normal box score filter, you fade out these corner reflectors. And if you use a deep filter,
You keep.
this corner.
Yeah. That's.
So is this term fading related to this filtering operation?
Sorry, I don't.
Term fading,
The term varying,
fading.
fading. Okay.
Is it related to this filtering operation, the leaf filter or the?
You give an equation for an intensity where sigma the mean value-
Multiplicative noise model
Yeah.
that you
Yeah.
give there, it is
sigma
written as
texture and that
fading
random
random variable
That
or
is all.
speckle part. Yes.
Ah,
Correct. So he's referring to that, whether that fading.
the texture, you mean? Oh. No, normally there are no specific filters to the texture. I mean, because the texture is something which is a scale you automatically preserve with the filter. I mean, there is nothing specific for the texture beyond the estimation of the moments that characterize this texture. Okay, maybe later on we can chat about this specific.
Can you just give an insight how that texture is multiplicative from physical understanding perspective?
No, for the physical, there is no physical. Everything comes from the mathematics. It's a model I apply to understand. I mean, you can understand as a multiple scales model. I mean, this morning we saw a very nice presentation about hierarchy scales. So here is the same, but it comes from the mathematics.
Like for speckle, you gave that linear.
Yeah, it is a mathematical model.
So all filtering that you referred to is at the real and the intensity level, right? There is no, or there is some.
No, all of them are applied to the complex.
At the phase.
Yeah.
Okay, these are real images from other examples that.
Yeah, because I only show intensity.
You mentioned that for partially developed spectrum, which will be L greater than 1, and L which is much greater than 1, which is a fully developed spectrum, where you assume a Gaussian model.
Yes.
For a L greater than 1 also, we assume the Gaussian model and we derive the theoretical equivalence of the
No,
movement.
No, for L between 2 and for a small number of. No, the problem is that there is no analytical model, but also you cannot define a statistical model. It's something in the middle. You cannot define something. I mean, the only way to solve that is analytically, but there is no analytical solution.
Okay. So, I mean, I just wanted to correlate that they both still assumes a Gaussian model. Isn't that?
No, you assume a Gaussian model when you have a large number of targets in the resolution cell. It's the other way around.
So here we cannot generalize that.
No.
The L greater than 1.
No.
Which model to be assumed?
No. The idea, L equal to 1, no speckle, no distribution, perfect. L infinite, ideally, Gaussian model. In the middle, I have no solution. We cannot generalize GOPA. You can start to play with more complex distributions, but they are very complex. And very difficult to handle. They depend and very in higher order moments, we need a lot of samples to be estimated, etc.
The flowchart that you show, the theoretical equivalence, and we finally derived this Richard
Yeah.
PDL.
Only applies to distributed totally fully developed spectrum. So only applies to that. Only for fully developed spectrum, because it's the only case where I can assume the Gaussian distribution.
Constrained to the resolution, right?
Yes.
So if we consider an
Let's put it in a different way. I can assume Gaussian here. In here, I cannot assume Gaussian.
In cells that you take and you distribute it in, sorry, you plot a histogram to check whether it is Gaussian, or you just take a one range window.
No, all of them. So the way to analyze these areas where you have points and distributed targets, I mean, you at the end, despite it's not the best, you apply a distribution, but it's a much more complex distribution, especially with long Q, in order to accommodate all those bright points or all those targets. So basically, our super complex distribution that to accommodate in a queue those bright pixels. So basically, it's a way to combine on the same thing point and distributed targets. You try to combine one of them. I mean, it's something quite complex to understand. But basically, I'm not in this case, L equal to 1, I'm not in the Gaussian case. Okay, so what I can do, I try one distribution that is able to cope with both at the same time. So normally, as point targets have bright points, I try to apply distribution with a long Q. Try to accommodate the distribution of these point targets.
Like long tail.
Long tails, exactly.
Are you in a position to select a certain region for that? Okay, we can say, okay, this region probably belongs to a Gaussian distributed versus a non-Gaussian.
Yeah, normally these areas which are super flat, super homogeneous with no variation, they are Gaussian. So take one SAR image, download from anywhere, take one homogeneous area, and you calculate the distribution. And you will see that it's a Gaussian distribution.
There could be a position where you select a region which is overlapping between the homogeneous area and the heterogeneous area. So
no,
again, it lands in
yeah.
non-Gaussian.
As I said before, the Gaussian model only applies to homogeneous areas. This is all except homogeneous. So that's why I need a more complex distribution to analyze these areas. Okay, it's a complex thing. Therefore, at the end, I mean, I didn't want to talk about this, but let's go. It's super complex. So the way all the filters try to cope with this issue, instead of trying to use complex distributions, they are designed with the idea to keep the spatial resolution, to keep the details of the image. Therefore, you don't have to cope with that distribution. So therefore, your filter doesn't need to estimate moments of the distribution. The only thing the filter needs to figure out is, am I in a homogeneous area or am I in a point target where what I want to keep is the spatial resolution? Okay, the most advanced filter, as far as I know, is the non-local filters by some colleagues in France, but it's super heavy to, I mean, it can take ages to filter one image because it's, okay, the result is perfect, it's super nice, but it's super slow because it's super complex. Okay. Questions?
Simultaneous target detection and denoising, because noise is a big factor of targets. So if there is some kind of a trade-off available, we can estimate target automatically, and then
that's what I said before. All the filters try to cope with that duality. At the same time, they try to maximize filtering, and at the same time, they try to keep the spatial resolution. So how do these filters deal with this compromise is the design, of the algorithm.
Homogeneous targets by default are relatively larger than point targets.
Yes,
So
that's the definition itself.
yeah, so does like filtering, like in terms of interpretability, the benefit of filtering for interpretability of our image, does it really add value? Because now we are
Okay. I will wait a little bit and you will see in the last part of the presentation. Okay. So what I would do now, I would skip the last part, okay, of this presentation. I wanted to present some new models we defined long ago for multidimensional. I prefer better to skip that part. You will have the material. If you have questions, just send me an email. And I would like to switch, if you want, to the next presentation where we see the connection between all the things. I think that part is more important than just to go on the specific particular filter.
that example you gave here, L is 1, L equal to 1000, where you increase the number of targets in a range distribution cell. That's what you did.
Yeah, I increase the number of targets in the resolution cell. Yeah, 1, 3, 5, 10, 100, and 1000.
1000 targets within a cell.
Within a cell, yeah.
That's what you were.
Yeah, that's L is the number of targets, okay?
All targets are homogeneous.
Yeah, homogeneous, yeah. Very simple, it's a very simple, but you can see, okay? So let's go to the next. So, okay. First presentation, polarimetry, okay? And at the end, we saw the map where we lost the connection between the scattering matrix because it's the matrix where I have the proper physical interpretation. I know how to interpret that, but due to the speckle, I need to break that relation. So therefore, it appears the C matrix. How I recover this physical interpretation? Okay, how do I physically interpret the covariance matrix? Okay, so this is the topic of this last part of the course. Later on, together with Armando, we will deal with some examples and you will see how it works with the algorithm. Okay, again, the information. Okay, so techniques that will allow the recovering of the physical information is called, or they are called, polarimetric target decomposition theory, which indeed is the most basic tool for physical interpretation of polarimetric data. And also, life is something more than dihedral, trihedral, and spheres, okay? In real life, we don't have that. We have something more complex. So how do we interpret physically this complexity? Okay, so the idea is to decompose our signal, okay? The idea is the following. Whenever I have the scattering matrix, I can talk about what is called coherent decomposition. So my idea is to decompose my real scattering matrix in an addition of some canonical scattering matrices which I can physically interpret. Is divide and conquer. Okay, if I don't know how to interpret the real scattering matrix because the target is very complex, let's divide it in an addition of simple scattering mechanisms which I can interpret easily. For incoherent decomposition, it's exactly the same, but I don't decompose the scattering matrix, but I decompose the coherencies or the covariance matrix. An advice, these decompositions only apply to the scattering matrix, so only applies to those targets where I don't have a speckle. So it only applies to target or to totally polarized waves. Covariance matrix or coherency matrix and the consequent on the subsequent decompositions only apply to distributed targets. Okay, you cannot mix more or less both. Okay, so let's go first with coherent decompositions. What I can do? Let's take the first, which is the Pauli decomposition. Indeed, we have already done that. I know that this matrix, okay, belongs to single bounds. This matrix belongs to double bounds, double scattering. This matrix corresponds to volume. Okay, so if I'm able to decompose the scattering matrix, the real or the actual scattering matrix I measured in this way, what I obtain is which quantity of single bounds I have, which quantity of double bounds I have, how much quantity of volume I have. And this quantity is determined by the weights, alpha, beta, and gamma. For the Pauli decomposition, it's super easy to obtain this alpha, beta, and gamma, because alpha, beta, and gamma are directly HH plus BB, HH minus BB, HV. So therefore, I decompose a real scattering matrix that I don't know how to interpret because it's real in something of basic building blocks. And therefore, I don't interpret directly this matrix, I interpret the coefficients, because the coefficients tells me how much of single bounds I have, how much of double bounds I have, how much of volume I have. Okay, so let's make it. Okay, this is very simple. Okay, so in the case of this image, so this is alpha, this is beta, and this is gamma, and this is the plot of these two. Okay, so therefore, if we look, for instance, in this area in here, this is surface scattering. Okay, so therefore you obtain surface in here, less of double bounds, and you don't have volume. This is what I see here. So I can interpret, for instance, that this area, okay, has very few volume. Okay, and for the rest is exactly the same. As you see, this decomposition is very simple. Okay, so it's useful to see which is the polarimetric information content, okay, and I can combine them in the color. So basically, this color composition is nothing more than combining these elements in here. So basically, what I'm interested is into the relative differences between them. So basically, in here, I have green, so it means that the largest value is volume. This is what is giving me here. Okay, in this case, the largest is red, which means I have double bounds. Okay, and the case in blue, for instance, which appears in here and here, or in here, it means that in this areas in here, what I have is surface scattering. Okay, so the idea basically of the target decomposition theorems is this idea in here. Okay, is to decompose all of them. Just because we have only 5 minutes left. Here is the Colocated decomposition, which basically makes the same. Okay, but let's go to the second case, which is the incoherent decomposition. That the idea is exactly the same. So the interpretation in the case of incoherent decompositions, what I make is to decompose the covariance matrix. Okay, in that particular case, I'm analyzing not a particular sample, but the average sample, because I remove a speckle. So therefore, I'm not analyzing a particular pixel. Okay, so what I'm trying to analyze, okay, is kind of average target. Okay, there are different decompositions. Okay, we have model-based decompositions in which I use a physical interpretation, or the mathematical-based decomposition in which the decomposition is imposed mathematically. Okay. In the case, this is a map of the target decomposition theorems. So let's go. I will skip this, okay, because this is not important. Okay. So the maybe one of the most important decomposition, because it's the first one, is the Freeman decomposition. So in this particular case, what the decomposition makes, okay, is to decompose the T and the C matrix into three elements: single bounds, double bounds, and volume scatterings. But in this time, expressed in terms of T matrices. So the model used is a model for the single bounds, which is given in here. So this is the model of the covariance matrix for the single bounds. For the double bounds is exactly the same. Here you have the model. For the volume is exactly the same. Here, this is the model, okay, I am using. Okay, so therefore at the end, what I can make is to decompose this matrix into this expression in here. The problem here is that I have 5 coefficients, but I only have 4 observed equations. So therefore, in this particular case, the decomposition is done in terms of some assumptions. Okay, if I make the assumptions, okay, I can obtain this. So here you can obtain a much better characterization of the data. So look at the distributed target, the forest. If I make the decomposition, what I see is that I don't have surface, I don't have double bound except on some locations, but what I see is a lot of volume. So basically, you can identify where do you have the volume. The volume, you have it in the bars, okay? So this is a way to interpret the decomposition. Okay, this is the composition. I can decompose between the double bounds, the volume, and the surface, so you can see pretty clearly where do you have volume. Okay, and just allow me to finish. Okay, which is we will go into the details, into the practical exercises, which is perhaps also one of the most important decompositions, which is the eigenvalue eigenvector decomposition. If I have a matrix, I can decompose the matrix into the eigenvalues and the eigenvectors. Okay, and this is the work done by Poitier and Cloud. Okay, so basically I can decompose mathematically into 3 eigenvectors and 3 eigenvalues, and therefore I can compose the matrix. The only problem of this decomposition, which works very well, is the physical interpretation of these elements in here, because it's a mathematical. It doesn't look at the physics. The problem to use this decomposition is on the physical interpretation of the scattering mechanisms in which I divide the matrix. Okay? Questions? Sorry?
How can we understand these decomposition for dual pole data? Like
This one. No, some of them for dual pole cannot be applied. The H alpha decomposition has a reduction to be analyzed on dual pole data. Okay, there is a paper on about Shane Cloud where he analyzed this decomposition for dual pole data. Yeah, there is it's a conference paper.
Partner reflector. I want to find out single bond double bonds like one in common, and I can't use Freeman.
No, you have to use the coherent decompositions. Kroger and Pauli. That could be an idea, because a target, sorry, a corner reflector is a point target. So therefore, you need, or you can apply either Pauli or, as you mentioned, Kroger, which is a variant of the Pauli decomposition. Okay. I recommend you to go to the book I presented before. There are many books, okay, but that book, the advantage is that it's free, so you can download all the chapters. You have the theory. You look at all the application, how people analyze different applications for forestry, for crops, for ocean, for urban. I think there are 4 chapters on for forest, for crops, for cryosphere, for urban areas, and for ocean applications. There are 5 chapters. Okay, go into the website and you will see.
Differ for the ground-based star imaging.
Sorry, repeat again.
The ground-based star
Yeah.
imaging. Will the same theory applies there, or
Yeah, we in our lab we have an ground-based star system and we applied all these techniques. They can be applied as far as the system is fully polarimetric.
That's an extension to that point target. Can still apply Freeman and Yamaguchi, right?
No, because if you apply Freeman, and the Freeman is that it is assuming that you have distributed targets. Freeman assumes that what you have is distributed targets.
Because you are working on second order, right?
Yeah, exactly.
What's your personal choice for this full polarimetric decomposition out of all these? Like, what do you recommend?
I don't recommend anything. I mean, depends on your application. That's the best recommendation. Everything depends on your application. So whenever you are facing one application, you can, by the way, there is this software Pulsar Pro, which is free. Some of you may know, you can look on the internet. You have all the decomposition, all the techniques, everything. So you can start. I do it myself. When I start with a new application, I take data, I look, I start to see which is the best, which is the worst. Everything depends on your application. What it may be very good for me, it may be very bad for you, and the contrary, okay? So there is an exploration exercise at the beginning.
You have observed that also.
Yeah, I in all my applications,
Multiple applications.
yeah,
One will work better.
than the other, yes.
That's what you have experienced.
At the end, what you are doing is combining things from here, things from there, things from there, okay?
Never experience. You should say, in this context, I get my decomposition. In this context, Freeman equation. In this context, can you say?
This is a compromise. Now, whenever I have distributed targets, forestry, I will go to the cloud Poitiers decomposition, more or less. Okay, but I'm reluctant to say something, but people normally takes this as a work of faith, and it's not that. Okay. Okay. So thank you very much. You will have the presentations, all the presentations later on, and if you have questions, don't hesitate to ask me during the conference or afterwards through email. Okay. Thank you very much.
All right. Thank you so much, Dr. Carlos. I hate to interrupt such a lively presentation, but we should move on to tea time. Yeah, and then we have the ESA workshop, even more exciting stuff coming up. So let me just present the memento to Dr. Carlos for giving a great tutorial here. I'm hoping all of you have benefited a lot from it, and we will be passing on the videos and material that so would be sharing with us. Yeah, thank you so much, guys.
Thank you. Thank you very much. Thank you very much.